Hey guys, it's AxiomaticUncertainty here, and I'm back with another video. And today I wanted to show you guys something neat that I've been working on a little bit today. And this is not totally finished, but we're going to go over how I did it and how you can do it. And then at the end of the video I'll go over my plans for future stuff. So you can see here this little sphere is moving along this sort of white track, and you'll notice if I sort of move this track around, I can change obviously the movement of the sphere along that track. So you can see it's now gliding along a different section of track. If I come down to this bit down here, I can also move this over, and you'll see it responds to that as well. I can even move these in real time, and it'll sort of follow along with that. And then one last thing I want to show off is this nice feature, which I've not noticed in a lot of these other Spline implementations in Unity that aren't, asset packs, which obviously I, as you may know if you already watched this channel, do kind of detest. So what it is basically you'll see it's a series of scripts. So we have the Spline manager script and then a number of others, and you'll see if I set this up and assign this third capsule, it now is already configured to work. Now if I go into capsule 2 and I change this outward magnitude, you can see I can get some really nice curvature very easily. Capsule 3 is obviously pointing this way. If I make its backward magnitude 5, for example, or even 2, you'll see it changes the way in which the curve acts. So you can see at the end we have this little hump here. And the larger I make that value, the larger that will get, obviously. So those are the magnitudes of the tangent. And now we're going to get into a demo, or actually an explanation of the actual code behind this. So it's a little bit spaghetti right now, but we're just going to go over the basics of how this is all working. We're not going to go too much into how it's being drawn, because I think that's not really core to how the whole system works. Sorry, I just was taking a swig of soda. But basically, this is a class that we have inside of our Spline class. So the Spline class is an easily extendable class that you can attach to any object in order to create a spline, and then ideally you can make these capsules children, so that, as you'll see right here, if I move around the spline itself, or if I rotate it, the children move with it, right? So I can do all of that in real time. And it's pretty effortless because of that implementation detail. So if you're using this kind of setup, I would recommend parenting a spline object, so that all of your, whatever these game objects may be that have the vertices in them, so that all of your vertices can easily move around as one unit. Alright, so getting into the specifics, what we have here is a few different bits of code. So the first and most important is obviously our Spline manager. Now, you can see we have a vertices game object, and we have a renderer prefab. This is no longer necessary. I just haven't deleted that yet. And this is not necessary either. And then we have a renderer and a pieces list as well. This is not public because our pieces are determined based on the vertices, which are what the user sets. So we're going to ignore the rendering portion for this video, just because that's, kind of superfluous. There are tutorials out there for that. We're going over this novel piece of information, so we'll focus on that. So getting into that then, the vertices are calculated during every update step. You could set these to be calculated, once every 10, or during the start, or just using some kind of calculate button embedded in the inspector or something like that. You could do anything. You could put this in a function and just call it as you please. I just have it here right now because that's all there is in the update function. So every time we run a frame, I clear this pieces list, and you'll see what these piecewise cubics are in a moment. I clear the pieces, and I go through each of the vertices -1, because each time we're going to get a pair of vertices, starting with the first one and the second one, and going all the way to the second to last and the last. Hence this decrement on the count. And we're going to go through and add a new piecewise cubic class instance, right? And we're going to pass these things to the piecewise cubic, and I'm going to go over how piecewise cubic works in a second. And then the rest of it is just rendering. So we, set the rendering positions, and yeah. So we're going to go into the last helper functions in a second, but first I want to talk about this piecewise cubic in a little more detail. So piecewise cubic is the result of, a little bit of messy code, but also some thought on my part about how I wanted to do the spline. Splines obviously involve quite a lot of math, and when I was researching current implementations of splines for a project that I had wanted to do, personal projects, I was unable to find a good concise equation. So what I ended up doing is just coming up with, and obviously this probably is a novel, I was just too lazy to find something good. This parametric equation, basically you can take in parameters for your tangents and your positions for the two vertices, and then it'll calculate a cubic parametric equation in 3 dimensions between those two. That may seem complicated if you don't have a lot of experience with higher level math, but just take my word for it. It does what we need it to, and basically what we pass to it is the position of our first vertex, position of our second vertex, so xf being final position, xo being initial position, or x naught, and then we have dx naught, which is just our initial delta, so our tangent at the initial vector, and then our tangent at the final position. So these are all the pieces of information we need. Then we take these in and we make some calculations for our parameters for our equations, and then every time we want to calculate a point on this specific section of our entire spline, we can just call this calculate point on our instance of the piecewise cubic, and it'll return the cubic equation relating to these parameters. So that's basically what this class is doing. And so obviously when we instantiate these basically hold all of our readily available mathematical information on this spline. And then for rendering, we just basically go through each of the piecewise cubics and we check 50 points across the entire interval, and then draw those. So now we're going to go into this last part here. As I said, there's not a ton that needs to be covered in this class, and basically what we're doing here is we're calculating a position based on a general parameter t. This gives us an overall position on our spline as a single parameter, and it does all the piecewise calculations for us. And I'll go over what the problem with this is right now in a moment, and then I'll talk about how I'm going to fix it and we'll go over some other things. So basically, the pieces are checked. So we check first if pieces.count is greater than 0. This is because if you call this function before you've set any pieces, which may happen in some cases, and happen in my code, hence my adding this, mostly out of laziness and desire to avoid having to fix my other code, because I did write some helper code in slide.cs, which we'll go over in a second, that just demonstrates how you can use this functionality. So basically, if we have pieces, we're going to run this section. Otherwise, we just return the 0 vector. It seems like the natural solution. So if we have pieces, we will return basically the position on the spline. And the way in which we calculate that is, first we calculate this x, which is basically t but scaled to the number of pieces. Obviously, as I mentioned, this is parametric. If you don't have any knowledge on parametric equations, basically this piecewise function goes from 0 to 1 for its t, and so when we scale this up to the relative to the number of pieces, we can determine two things. So first, in this giant condensed return statement, we determine which t, or sorry, if t is less than 1, the issue being that t can be greater than 1 in some cases, in which case we just sort of want to effectively clamp it, and then we want to go through our pieces here and effectively take the floor of our x value. What this does is it gives us the number of the piece that we're looking at, because as I said, this scales up to account for basically the sum of all of these parametrics, right? So if you imagine that you combine all these piecewise functions, function 1 goes from 0 to 1 in this new function here, and then function 2 goes from 1 to 2, and then function 3 goes from 2 to 3, right? So if we get the total range based on that sum, right, which would be our pieces.count, since each one has a length of 1 effectively in terms of its range, and then multiply that by the fraction of that we're covering. Basically, since this one goes to 0 to 1, from 0 to 1, it gives us a fraction of the total spline that we want to cover, and that whose location we want to get. And then we calculate, based on the piece that we've retrieved, the position of the piece that the position that we're trying to find on that specific piece, right? So we get the piece that we need, and then we take x minus the floor of x, right, which gives us basically the portion that's in the range of that piece, right? And then we calculate that point. And then this part is just if x is greater than 1, we basically just want to calculate. This is an override, is actually how I'll explain it. If x is equal to or greater than 1, this just breaks because it's going to try to index to a piece that doesn't exist. And so the fix for that is basically just to force it to clamp to the position of the last vertex on the spline if it's greater than or equal to 1. And then obviously I already went over that portion. So that's all the functionality for the spline. I hope you didn't get too lost. My explanation sort of meandered a little bit there because I hadn't thought this through totally how I was going to explain this. That is, and I've been working on this for a little bit, so my thoughts have been kind of jumbled. But then this part here is just for each vertex we can, throw this script on, and basically the spline will then retrieve the forward and backward magnitudes at the tangent. So that's basically the, as I said here, that's the degree to which a tangent, pushes out from its origin. So you can see here, if I go in here so you can see this a little bit more easily, if I were to increase magnitude forward, you can see it adjusts up because increasing that increases the strength of this tangent. So that's kind of the gist of it. And then slide.cs. So this is basically a demo of how you can use these splines. If you want to just copy my code, though I don't recommend it because I tend to tell people, just try to understand it before you do that. I'm a big advocate of trying to actually, learn things fully instead of just doing the plug and play approach that seems to be very popular these days. And so what I do here is I create a float called T, and you'll notice we also have a spline here. So the slide class takes in a spline, right? This is, again, just a demo. And slide is attached to the sphere. So the sphere has an instance of spline. And at start, it sets its position to 0. And then basically every update, it increases t by time.delta time divided by 10. Time.delta time obviously gives you, a fraction, that will, it's essentially 1 over your frame rate, right? It gives you a fraction that when summed over the course of a number of frames gives you the current time, or, the sum of those changes in time. And this is useful for us because then when we divide by 10, we're essentially giving 10 seconds of time for it to get across the entire spline. So if you don't understand time.delta time already, you can look that up. But basically, it's just a way of creating time invariance in, scaling some value. Or frame rate invariance, I should say. And then here, we basically just check if our t has gone over 1, since obviously our parameter only goes to 1, right? We can only go from 0 to 1 as a fraction of the spline. And so then we go back to 0, and that's why, as you saw, when it gets to the end of the spline, we just reset back to the start, we just keep looping through. So basically, this is just a demo of, how sort of you can use these splines in your projects and how they can be useful. Obviously, they're very flexible, very extendable, and I hope to get these to be a little bit more functional, but, they work pretty well, and they're nifty, and I think they're going to be able to serve my purpose for them. So one last thing I want to cover here, just, while I have you, is what change I want to make that's going to help and why you shouldn't use them in their current state unless you have, some specific understanding of the way in which this works. And I'm going to demonstrate this in real time just so you can understand this a bit better. But the issue, the crux of it, that is this can be adjusted out. But what happens is the movement speed, so you can see right here, we speed up as we get across, versus this section of track where we're moving slower. Even though, in theory, if we're doing a fraction of the track, that shouldn't happen. Now, the reason for that is that, as you can see here, our sections are between these vertices, right? So this section is shorter. Now, as I mentioned earlier, all this parameter does when we add it from the sphere, right? When this t value goes, into our splines function, all the spline does is it checks, in this case, there are 2, right? So it checks is this greater than 0.5, right? And if it is greater than 0.5, we're going to be on this section. If it's less than 0.5, we're going to be on this section because there are two of these. It assumes basically that they're the same length, and then it selects a percentage of this one based on the remaining section. So it would basically say minus 0.5 because it's greater than 0.5, and then it'll check where on this one it is, as we mentioned, based on how those actual functions interact. But the problem is, again, that these lengths are not fixed. They can be changed between sections, and that is a big problem in terms of being able to get reliable functions out of this, because obviously usually you're going to want this to be based on the length of the track and not based on arbitrary sections determined by the vertices. And so in order to fix that, I am going to scale all of the functions based on the length of the sections of the track. So I'm going to do that at some point. Obviously I haven't done it yet, and I probably won't be able to get to it today. And then once I've done that, I'll probably post the code on my GitHub, so you'll be able to find it there. I'll put the link in the comments if that's done, when that's done, I would hope. And yeah, that's, basically it. I don't know, I couldn't find any good splines in Unity, so this is my, current attempt. And, yeah, I hope you enjoyed it. If you liked the video, please, remember to subscribe, comment if you have any video ideas, and like the video if you enjoyed it. And, yeah, that's going to be it for me, guys.